3, 2, 1. Hi folks, it is Dr. Zanzo here, and I'm going to, in this video, go through some of the most frequently missed questions from this semester. What is this all about? Well, when you all take the exams, I look at the data from who did well, who did not do so well, and then I also look at the questions, and I look for questions that almost nobody got correct. And I assume that if almost nobody got those questions corrected, by that I mean more than 60% of the students got them incorrect, I assume that there is a problem either with the way I wrote the question or the way I taught the concept behind the question. So what I do to sort of reconcile that is I will subtract those questions from the total, throw out those questions, so to speak, from the exam, and then I will review them with you, and then those questions are going to show up again on the final exam. So, for example, on exam 1, there were 45 questions. If there were 4 most frequently missed questions, that means there's only going to be 41 questions that are going to be in your denominator. So if your original grade was 30 out of 45 or 67%, then your new grade would be 30 out of 41, which is your new denominator, which would give you a bump of about 7%, 6%, somewhere in there. So that's the way this works. What if you got the question right the first time? It doesn't matter because I don't actually go in and calculate who got it right and who got it incorrect. Everyone gets a boost from this, whether you got the question correct or incorrect, because it's just simply coming out of the denominator. So everyone's grade gets improved if you got the question correct or incorrect the first time around. All right, so the same concept, but not exactly the same question, is going to be tested on the final exam. So the questions on the final exam are worth more points, which means you should get them right this time around if you understand the concept, if I relate them to you better. Or in other words, if I fool you once, that's shame on me. But after telling you that these questions are going to be on the final, if you get it incorrect a second time, well then shame on you. And that suggests to me that you don't understand that concept. Okay, so with that in mind, I'm going to make a playlist here going through exam by exam. First exam covered introduction to biology and biochemistry. Most folks did just fine on that introductory material, understanding the basics of what it means to be alive, but the biochemistry kind of threw us for a little bit of a loop. So here's our first most frequently missed question that will reappear in some form or fashion on the final. We've got fructose. This is fructose over here. And we've got a bunch of terms that may describe this molecule. And what this question is going after is, do you understand how we categorize different simple carbohydrates? And one way we can do that is by grouping them into aldoses and ketoses. That has to do with the position of this functional group here, this carbonyl functional group. Is it internal inside the carbon chain, or is it terminal? Is it at the end of the carbon chain? And you can see here that the carbonyl, the C double bonded to O, is between 2 carbon atoms. So that is a ketone, not an aldehyde, so it is in fact a ketose. Okay, so that's one way we can categorize simple sugars. Another way is by counting the number of carbons in the backbone of this molecule. And here we've got 1, 2, 3, 4, 5, 6. 6 carbon sugars are also known as hexoses, so both A and B are descriptive of fructose. Let's jump down to D. I already suggested this is a simple sugar as opposed to a complex carbohydrate, something like starch or cellulose or chitin. Those are all complex carbohydrates, so this is a simple sugar, which leaves us with a disaccharide. A disaccharide is a dimer or a two-part molecule of two monosaccharides. So how do we recognize whether we've got a monosaccharide or a disaccharide? And the answer is we look for a glycosidic linkage. So carbohydrates, hopefully you recall that they are connected to each other by what are called glycosidic linkages. So it kind of looks like they're holding hands by this oxygen atom here. But this here is the glycosidic linkage. What we're looking at here is sucrose, or table sugar, which is a disaccharide. It is a dimer of glucose and fructose. So the answer for that question is this is not a disaccharide. This is a monosaccharide. See, there's no glycosidic linkage. There's no two carbons holding hands via an oxygen atom. Okay? Moving on. Okay, so then I said, let's try and apply some of our knowledge and see what we know about a molecule that maybe you've never seen before. This is cortisol, which is a hormone that's associated with organisms under stress. So I thought maybe you can relate to this in some way, maybe not intuitively, because biology doesn't work that way. You have to learn the concepts before you can apply them. So here's another one which is asking about the incorrect statement, and with all of them being correct being a possibility. So, is it a steroid? How do we define a steroid? Remember, a steroid is a molecule that has this distinctive four-ring structure. So, three 6-membered rings, 1, 2, 3, and one 5-membered ring. And so that is a steroid, and we have a number of them that are biologically active in our bodies. For example, testosterone, estradiol, cholesterol. These are all different types of steroids. And the steroids that you might get if you're really sick and you go to the doctor and he or she prescribes you a steroid to help you get better quickly, or the steroids that athletes take to increase their muscle mass. They have this same basic shape. So yes, this is a steroid. What do we know about steroids? They are all lipids. All steroids are lipids, so A and B are both correct. What defines lipids? Lipids tend to be very much dominated by just carbon and hydrogen, hydrocarbons. And they tend to be hydrophobic because of that. They may have a few other functional groups on them, but the bulk of the molecule is hydrocarbon. And so steroids are lipids. All steroids are lipids. Not all lipids are steroids, but all steroids are lipids. So those two are correct. What about C? Is it an alcohol? How do we recognize an alcohol? A couple of ways we can recognize an alcohol. If we look at the molecule, we look for a particular functional group, which is a hydroxyl group. Here's a hydroxyl group. Here's another one. Here's another one. So this is 3 times an alcohol. So that is correct. Also, cortisol ends in OL. And molecules that end in OL, typically that means it's because they are some type of alcohol. OL, alcohol. All right. So that leads us to option D. It is a ketone. What is a ketone? A ketone is a type of carbonyl bond, carbonyl, which is C double bonded to O, as we saw in fructose, inside of a carbon skeleton. So it's got carbons on either side of it. And what we see down here is O double bonded to a C under here, between 2 other C's. So yeah, it is a ketone. Or we could look at this one up here. This kind of looks like a carboxyl group, an organic acid, but it is not, because there's an extra carbon between this carbon here and the hydroxyl group that's here. So this is actually a hydroxyl group, carbon, carbon, and then that's a carbonyl functional group. Okay, so the correct answer is that all of these are correct. Okay, so if that one gave you trouble, this one probably also gave you trouble. How many asymmetric carbons does cortisol have? And how do you recognize asymmetric carbons? Well, an asymmetric carbon is defined as a carbon atom that has 4 different substitutions. And the substitutions are the molecules or atoms that that carbon is connected to. So the hard way to determine how many asymmetric carbons there are would be to look at this molecule and draw in all of the carbons and hydrogens that are present. So there'd be a carbon here, carbon here, carbon here, carbon here, and then counting up bonds and saying, well, this carbon only has 2 bonds, so it has 2 hydrogens on it, and drawing in all the hydrogens. And that is a big pain, and there is an easier way. And that easier way is by looking at these things, these wedges here. So these wedges that come out that are solid, that means that this functional group, this methyl group here that isn't drawn in, is coming out of the plane of the page at you, and these dashed ones are going back into the page behind you. So the reason that they show that as coming into the page or out of the page is because it matters, because it is an asymmetric carbon. So we can count the number of carbon atoms that have wedges on them, and that will tell us how many asymmetric carbons there are. So like for example with this hydroxyl group here, you can see it's not wedged because it doesn't really matter. It can rotate around this axis here, and it's not asymmetric because there's 2 hydrogens on this carbon right here. So let's count the wedges. How many do we see? 1, 2, 3, 4, 5, 6, and then this carbon here has 2 substitutions, one that's coming out at you and one that's going back into the page behind. So that's number 7. So the correct answer is that there are 7 asymmetric carbons. And I know you probably are thinking, how am I going to learn this? And the best way to learn is to practice. So I will give you some practice at the end of this particular video. Following up on that, I also showed you gamma aminobutyric acid, or GABA, which is another neurotransmitter, as is cortisol. While cortisol is associated with stress, GABA is associated more with a feeling of calmness. Yes. So again, this time I flipped the script and said, which of the following is actually correct as opposed to not correct about GABA? So one of these things is not like the others again, but we got to figure out which one is not a lie. All right, which means we have to be able to recognize different functional groups. Is it a ketone? Well, a ketone, as you might recall, is a carbonyl group that is inside of a carbon skeleton. So here's a thing that looks kind of like a carbonyl group because it's C double bonded to O, but it is not in the middle of a carbon skeleton. It is actually attached to this group here. And all of this group together, it is not a carbonyl group and a hydroxyl group. This is an organic acid, which functions very differently from a carbonyl group or a hydroxyl group because these 2 oxygens are pulling electrons away from the carbon here, which means that this proton on this OH here can be donated to solution. Molecules that donate hydrogens to solution are acids, so that's why this is an acid, an organic acid. So it is neither a ketone nor is it an alcohol. Is it a carbohydrate? Which we'd be looking for in a carbohydrate. We already saw this We should be looking for a carbonyl group, and we should be looking for hydroxyl groups, and we see neither of those here, so it is not a carbohydrate either. It is an amine. Here's the amino group, and the name suggests that there would be an amine group in it and an organic acid group on it. So that leaves us with one option, that it has 4 carbons. So let's see, let's count the carbons. Here's 1 carbon, 2 carbons, 3 carbons. There's the 4th carbon, and then there's the amine group there. So it does have 4 carbons. So the correct answer for this guy is B. Okay, so how do we recognize asymmetric carbons? How do we recognize functional groups? Well, for the kinds of questions that you're going to be given on the final, it would help to get some practice in. So I'm going to give you a little practice right here. So I got these next few images from this really awesome website, compoundchem.com, which has infographics about all manner of things chemical, biochemical, chemistry of Christmas tree smell and new car smell, and chemistry of all kinds of different interesting things you may encounter on a daily basis. But these images I took from one of their pages on vitamins, and I did show this in lecture, but just very briefly, so I'm going to kind of zoom in on a few of these vitamins, and I want us to look for functional groups, and I want to look for asymmetric carbons. So for the asymmetric carbons, you're going to look for wedges. Remember, a solid wedge means it's coming out of the plane of the screen at you. It's an outie. And a dashed wedge means it's going back into the screen away from you. It's an innie, okay? So let's take a look and see. And you maybe have heard of some of these vitamins before. All right, here is vitamin A. Vitamin A is found in carrots and a lot of your orange vegetables. It is naturally kind of an orange color. This helps with your eyesight. So let's look for functional groups. Do we see any functional groups? Well, it ends in OL. That suggests it's an alcohol. And here is that hydroxyl group that lets us know that, yes, in fact, it is an alcohol. Any other functional groups? These dashed line, or this, not a dashed line, this line that's hanging down here, and here, and these rabbit ears up here are all attached to methyl groups. Now, you see these methyl groups hanging off of there, but they're not wedged. They're not shown as coming out at you or away from you. There's a good reason for that. It's because they're not asymmetric carbons. You might say, well, you've got these 2 methyl groups on here, but they're equivalent to each other because this is a CH3 and that is a CH3, and so they're chemically equivalent to each other. Another thing that tells us that we don't have an asymmetric carbon, any carbon that has a double bond or a triple bond cannot be asymmetric because it can't be bonded to 4 different things. They all have to be single bonds. So as far as functional groups, we've got the methyls, we've got the alcohol, but zero asymmetric carbons. Okay. Here's vitamin B7, also known as biotin. Very important vitamin that we need in our diet. Actually, we don't need it in our diet, but we have it produced by bacteria that live in our intestine. So let's see, do we see any functional groups? Well, here's an S, which suggests we've got a thiol. We've got a couple of amine groups. We've got an O double bonded to carbon, which means that's a carbonyl group, although it's going to act a little bit differently because it's got these 2 amine groups attached to it. And then over here we've got this guy, what is that? Are you talking to your computer? I can't hear you. But this is an organic acid right here, C double bonded to O and then OH, so that proton can pop right off. All right, so those are the functional groups. Now let's look for asymmetric carbons. Do we see any wedges? Yep, we do. Here's a wedge here, here's a wedge here, here's a dashed wedge there. And that tells us that there are how many asymmetric carbons? 1, 2, 3. That's it, just 3 on biotin, which isn't to say they're not important. Small numbers don't mean unimportant numbers, but not a lot. Here's vitamin C. You've probably heard all about vitamin C, and maybe you take it when you're starting to feel sick to support your immune system, but vitamin C has a number of uses in your body. And this is what it looks like. So it is ascorbic acid. That suggests that it is an organic acid. Where is that carboxyl functional group? Well, as it turns out, that carboxyl functional group is right here. But that oxygen has lost its proton and it actually attaches to a carbon right there. Any other functional groups that we see in here? Bunch of hydroxyls. Ho, O, O, O. Okay. Any other functional groups? Those are no, not really. But do we have asymmetric carbons? Look for the wedges. How many wedges? One wedge coming out at you, one wedge going away from you. That's 2. 2 asymmetric carbons. Okay, I'm going to show you the next one. I'm going to shut up for a second or two, and so don't be scared that I am capable of shutting up. Here I go. So this is vitamin D. Cholecalciferol. Looking for functional groups. Well, I see one functional group. And the name for vitamin D, cholecalciferol, suggests that you would expect that on there. And that's this hydroxyl group up here. All right, so we can see a whole bunch of just carbon and hydrogen. But are there any asymmetric carbons? Yup. Here's one wedge, 2 wedges, 3 wedges. So there's 1 asymmetric carbon, 2 asymmetric carbons, 3 asymmetric carbons. All right. So you might say, well, what about these 2 methyl groups that are hanging off the end here? Are they asymmetric? No, because they're not dashed for one, and they're also chemically equivalent to each other. A methyl group is a methyl group, so you can just show them as being in the plane of the page. They don't have to be coming out or going into the page. So that's vitamin D. I think I've got one more, and that will be the end of my video on Chapter 1, Unit 1, Most Frequently Missed Questions. Okay, vitamin E, famous for being good for skin. So alpha tocopherol suggests that OL, there's a hydroxyl group on there. There it is. And then you've got this O in there, but that's a member of a ring, so it's not strictly speaking a functional group per se. But do we see asymmetric carbons? Hopefully you do. 1, 2, 3 asymmetric carbons in vitamin E. So I encourage you, if you've got a minute, to go and look at Compound Chem and see if you can find functional groups and asymmetric carbons, because I'm certainly going to ask you about that on the final. All right, up next is our Unit 2 exam on cells and cellular processes. Oh, wait, let's see. So from exam 1, there were 4 most frequently missed questions, which means your new denominator is 41. So however many you got correct the first time, divided by 41 rather than 45 will give you your new score times whatever the multiplier was. I think it was worth 125 points. So that's where your new grade would have come from. 1, 2, 3.